Hello, everybody, and welcome back to the Spanish Pavilion, the space that we are having here for Spain-based tech companies to showcase their business, their knowledge, their innovation. The next company that is going to present for us is Aeinnova, Alternative Energy Innovations. We've got with us Raúl Aragonés Ortiz, Business Development Manager of the company. Welcome, Raúl.
Thank you.
And the title of the presentation is Self-Powered Industrial IoT Monitoring Systems. So
Thank you for the
whenever you're
introduction.
ready, you're welcome.
Thanks to everybody for joining us, people from internet and people from the event. I'm Raúl Aragonés. I'm one of the founders of Alternative Energy Innovations. And our mission basically it consists on transforming the industry 4.0 into more sustainable and into more digital with the least environmental impact. So let me introduce how works this technology. First of all, just to take into account what is the impact of the downtimes inside big industries. So all the leakages, all the failures in all the processes that are in the industry 4.0 corresponds a totally lose yearly from 5% to 20% of their revenue.
Okay.
So it's very important that they need to improve their maintenance to increase their benefits. Well, and what is the mantra of this sector? Basically, the right part at the right place at the right time. So this is the best way to improve your productiveness and become more profitable. But well, to achieve this point, we need at least to overpass the three typical ways to improve your maintenance. The big one is the reactive maintenance. So when a process breaks, you repair it. This is the worst way to become productive nowadays. But well, in several industries, it's the only way to become more profitable. The second one is a preventive maintenance. This is basically the same as you do with your car. That every 15,000 kilometers you need to replace parts, independently if they are well or they are damaged. But you need to do this process. And the last one is the predictive maintenance that says you are capturing data, values data, rich data from your process, and you apply any kind of predictive, take into account this data you have been captured. And maybe you can enlarge the life of this process, maybe you have to reduce the life of this process, and you have to act in the process. And for doing that, you need rich data. That means a big amount of data. And this is not very easy nowadays using the traditional IoT devices that you can find in the market. Well, what do you see here? This is a typical oil refinery, and what is common in this kind of facilities basically are the heat. You see heat everywhere. Just to take taking numbers, practically the 20% of the energy of the European Union, the 20% of the energy of the European Union is lost in form of waste heat. Sorry. Practically the 60% of their costs are in form of waste heat. So why not to take benefit of this waste heat? It's a chance. At the same time, when you want to become more productive in this sector, what you find really in this kind of industries are the wiring. Every single meter of wires in this kind of sectors costs 50 euros. A big oil plant, a big chemical plant, has more than 1,000 kilometers of wire. So multiply this value per 50 euros per meter, and you will know really what is the investment in wiring. So basically, they only put wires in the critical processes, but the auxiliary processes are not really right now are not monitored. So heat in the process and a very big impact in the economy in form of wiring. They are not flexible. Well, when we speak about the Industry 4.0, we also speak about the Internet of Things. And this concept is very interesting to take into account. So Internet of Things basically means monitoring everything. And when you speak about monitoring everything, you are speaking about costs. Because every single device that are in the market wears batteries. And what happens with the batteries? Well, batteries, and in particular lithium batteries, are very bad environmental impact and social impact. So maybe you know that the majority of the part of the lithium is extracted from the triangle of lithium between Chile, Argentina, and also Bolivia, using indigenous people. That is a very important concept. To process the lithium, you need a lot of chemical, a lot of water, a lot of heat. So it's not easy to understand, but the environmental impact of lithium is very bad for the environment and for the social. But also, when you want to build a lithium battery, you need cobalt. The 45% of the cobalt is extracted from Congo in a semi-slave conditions for the people. So basically, when we speak about these big numbers from McKinsey, from Statista, that says that in 2025 there will be 4.3 trillion of IoT devices, if we have to think that every year we have to replace 4.3 trillion of lithium batteries, we said, well, this is not the right way to digitalize this kind of plants. So the future of the IoT for the industry cannot be using lithium batteries. In the first hand, basically for the costs. Every time you need to change a battery of any kind of IoT in the industry, costs between 200 euros to 300 euros per battery replacement. 200 to 300 more or less yearly. Plus the staff cost, the personal cost of changing the battery. Plus sometimes you need to stop the process to replace the battery, because maybe your IoT device is installed in an explosive environment and you need to remove the device to replace the battery in your workshop. So changing batteries has a direct impact in the costs. If you have, for example, a big oil plant with 10,000 devices, do you imagine 10,000 devices change every day? More than 1,000 battery changes every day. This is not practical. So what we present here is a new way of transforming that heat into clean energy. So that way, if we have heat in the process, if all of this industry like ceramics, iron and steel, aluminium, chemical, petrochemical, glass, brick, food, wood, so all of these industries that has heat in the process, why not to take benefit of this heat, converting this heat into electric power? This solution is not new. This solution has been introduced in the 1960s by NASA. So all the deep space missions like Voyager, Galileo, New Horizons, Cassini, all of these space missions are fully powered by heat, not by solar PV panels. For example, our colleagues from the new Perseverance rover that nowadays is exploring the surface of Mars, this rover is not powered by solar PV panels. It's powered by heat. So Aeinnova has patented a solution that comes from the space. Aeinnova is a spin-off of the microelectronics department of the Autonomous University of Barcelona that has been working in the last 15 years with projects with the European Agency of Space. So we have taken this idea that works in the space, but in this case for the Industry 4.0. So we create energy from heat. And what we present here is a new way of digitalizing the Industry 4.0. So we have two main solutions, what we call the waste heat recovery unit. This is a big device where we generate 400 watts of energy per square meter. So we have to compare more or less a solar PV panel that more or less generates 150 watts per square meter, more or less 5 hours a day. 5 hours a day. In this case, we multiply by 3 the power generated by a solar PV panel, but for 24 hours a day. So we multiply more or less per 20 the power total generated in one day. This is basically for creating clean energy that is returned to the grid, and basically this is what we call energy efficiency. In the second hand, we have the first batteryless and free of maintenance power by heat IoT device. We have several ways of communicating. It uses long-range wireless protocols like Narrowband IoT, LTE, Cat-M, and LoRa. It overpasses all the leakages of the IoT that are powered by battery. So the first limitation of the typical IoT that are powered by battery are basically the distance of communicating. They typically use Bluetooth, Wi-Fi ones, or for example, wireless car. They have more or less 20, 30 meters of distance. You cannot send data further, more larger, because you will need more energy to do that. And you can't do that because your battery is very limited in energy store. The second is the frequency of the data. You can only send data maybe once an hour, once a day, because you have more or less 3,000-4,000 of cycles of sending data. So if you separate them 1 hour, you have 3,000 hours of battery. If you separate them 1 day, you have 3,000 days of battery. But if you want to do measurements continuously every 1 minute, your battery will lose 3,000 minutes. That means 3-4 days. So typical IoT that are powered by battery cannot send data practically in real time. And finally, the typical IoT that are fully powered by battery cannot perform edge computing. Edge means processing, and processing means energy consumption. So typically, they capture data from the process and send data to the cloud, nothing else. So you have an important cost in your cloud platform. What I now present here is a new way of digitalizing this kind of plants, thanks of having a continuous energy source that is called heat. So we can send data at very large distance from 2, 3, 15, 20 kilometers, not 5, 10, 15 meters. We can send data practically in runtime. Every 30 seconds, we can measure data. So for your predictive maintenance algorithms, this is a very high important value, because as much data you have, more efficient is your algorithms being to be trained. And finally, we process data in the device, not into the cloud. That means a reduction of 90% of your cloud computing costs. So this data goes directly to our cloud platform that is called DAVIS, Dynamic Aeinnova Visualizer, where you have a lot of interesting tools, data analytic tools, graph tools, report alarms, and now in a couple of months we incorporate predictive maintenance algorithms. All of these projects has been funded by the European Commission. In this case, a live project for the European Commission that is called HIT-R, and in this case, Industry 2.0 from the European Innovation Council pilot. And how it works? It's quite simple. We have 3 elements: the thermoelectric generator that converts heat into electricity, the sensor, for example, vibration sensor, and the large long-range wireless protocol device that sends data very far to our cloud platform. So we need 3 elements. So what we can apply? We can apply predictive and condition monitoring for the machines. Like we have introduced before, between the 5 to the 20% of the costs of a plant are directly involved in a bad maintenance of the machinery. So let's try to apply this solution to pumps, compressor, steam traps, cranes, chimneys, filters. Anywhere where we have heat, we have at least 50 degrees Celsius, 50, we have the energy to power these devices. For example, this is a project installed in Bunge, a big multinational in the soybean sector, for measuring steam leaks in steam traps. For example, a typical oil refinery loses 3 million of yearly in form of steam. We are able to monitor, so this device harvests the heat from the process. Oh, there is no pointer. Okay. Harvests the heat from the process, measures temperature and acoustics, and sends data to the cloud. This is a self-power. It's autonomous. There is no battery. There is nothing to change here. You apply, and in a couple of minutes, you have the data in the cloud. Nothing else. Nothing to maintain. In this case, we are using LoRa protocol. In this order, this has been installed in Ferrovial Biogas Plant. This equipment is also fully autonomous. We have the thermoelectric device that is connected to the hot surface of a ventilator fan that it's at 70 degrees, I think. Yes. And then the IoT device, you plug it to the device, and finally the vibration sensor that is in the process. It's quite simple. You attach all the physical three elements, and voila, you have that in your cloud. In this case, you are also using LoRaWAN protocol. This is another plant. It's a chemical plant here in Spain, Ercros. It's an intermediate plant. It's very interesting to know this figure because it has the three elements: the thermoelectric generator converted to a steam surface, the IoT device, and the vibration sensor. In this case, also using LoRaWAN. We have other projects running in Safir, working with narrowband IoT protocol. That is the subband of the 4G and 5G for the IoT. This is a plant of Enel. It is a coal plant, a thermal plant. The same approach. We apply the thermoelectric generator, the sensor. In this case, we measure temperature, the IoT device, and finally, we integrate this data not also in the cloud, but also in the SCADA platform it's a network of PLC of Siemens. We can incorporate the data inside the entrant, the analog input of this device. And finally, all this network of data travels to the cloud platform that is deployed in Amazon Web Services. When the customer can create their own profiles, when customer can also in real time know what is the environmental impact of the network, because this solution reduces to the 98% the environmental impact of measuring data in a process compared to a digital device, a digital IoT device, fully powered via battery. So reduce practically to the 2% the environmental cost in form of just environmental impact. In form of costs, these devices cost more than 60% less to other IoT devices compared to Emerson, Honeywell, Rockwell, Yokohama. So it's cheaper and also has no maintenance. It's fully powered by heat. And that's all. Thank you for your attention.